Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Today we are going to be continuing our discussion of AP Physics 1, Unit 1 on our talk about projectile motion. This is our last video about projectile motion before we move on to our next concept in Unit 1. And there are a few key concepts that I really want you guys to intuitively understand before we do that. So in our last video, my fellow Beth walked you guys through a lot of the math that's related to this. So in this video, we're not going to be doing a bunch of math. Fear not. However, there are a couple of really tricky concepts that I want you guys to wrap your brains around. So stick with me. The first concept that I kind of want you guys to understand, concept 1 here, is that when we fire two projectiles from the ground at complementary angles, those are going to have the same range, or delta x. So what do I mean by that? So, well, first of all, complementary angles means two angles that add up together to equal a sum of 90 degrees. So say I have a little cannon here, pretend this is beautifully drawn, and I fire a cannonball, and I fire it at 60 degrees, and then I fire another one at 30 degrees. The total distance that those cannonballs travel before they hit the ground, that delta x, is going to be the same for both of those projectiles. And the reason why, that seems a little weird, that seems a little counterintuitive, but think of it like this. When I fire my cannonball at 60 degrees, most of my velocity is pointed upwards in that y direction, right? So I reach a greater total height, which means since I go up higher, it takes longer for me to hit the ground again. So I get more air time total, but my velocity in my x direction is a lot less. Remember when we talked about breaking down a vector into its different components? The x component of my velocity here is a lot lower because most of my velocity is pointed up, right? So even though I get more air time, my velocity in this direction is slower, so I end up landing here. Versus when I'm pointed at 30 degrees above the x-axis here, most of my velocity is pointed in the x direction, so I'm absolutely booking it as I move this way along the x-axis. However, because I don't have a lot of velocity in my y direction, I don't go up as high, which means I don't get as much air time because it takes less time for me to be pulled back to the ground by gravity. So even though I'm traveling faster, I don't have as long in the air, so I end up landing at exactly the same spot. So complementary angles are going to have, when fired from the ground, same total ranges that they cover. So that would be like 60 and 30 degrees, because 60 degrees and 30 degrees, 60 plus 30 is 90. That would also be true for 80 and 10, or 70 and 20, or so on and so forth. Any two angles that add up to 90, or are complementary, are going to end up giving you the same delta x in range. My little cannon situated on top of a cliff here. Woo, and we're gonna just draw my little cannon. Very artistic, very beautiful. And I fire a cannonball directly sideways, so no vertical component to it at all. So I'm just firing it horizontally. But then at the exact same time, I drop a cannonball directly downward, so it has no initial velocity in the x or y direction. These two cannonballs are going to hit the ground at exactly the same time. Sit on that for a second. If I fire a cannonball out of a cannon perfectly horizontally, and I drop one, no cannon involved, just dropping a metal orb towards the ground, they're going to hit the ground at exactly the same time. Okay, and the reason for it is this. Let's break this down a little bit. I know I promised you we're not going to do math in this video, and that's true. I'm not breaking that promise, but I am going to write just a couple numbers on the board because this is still physics. So here, when I fire my cannonball horizontally, it has no initial velocity in the y direction. So v naught in my y direction is equal to 0 meters per second. And here, when I drop my cannonball perfectly straight down with no initial velocity, it again has no initial velocity in the y direction. So my initial velocity in my y direction is also equal to 0 meters per second. So when I throw these into my UAM equations, into those projectile motion calculations that my fellow Beth walked you guys through last video, I'm going to end up that these get the exact same amount of time in the air. So then they hit the ground at exactly the same time. There's actually a really cool Mythbusters video on this where they not only demo this with like real things that they shoot, but there are like things being thrown, and it's very exciting, and it's a great video. I would recommend watching it. But this is a really counterintuitive idea that I really want you guys to wrap your brains around, because not only is it important, but it's also on the AP exam pretty frequently. The AP Physics 1 people love to ask about this. The other question that they love to ask about this idea is, which one is traveling faster? Well, they hit the ground at the same time, right? So they're in the air for the same time. Their change in time before they hit the ground again is exactly the same, right? However, this one has a farther total distance to go. So we have, this one just goes straight down, but this one has to cover this whole path and get all the way over here, right? Well, velocity is equal to change in distance over change in time. And we know they have the same change in time. So the one that has to go farther in that amount of time has to move faster. Does that make sense? Are you guys following me? It's kind of like if you wake up out of bed in the morning and you have 1 minute to get out of your bed. You can just sort of sluggishly roll out and plop to the ground, like this guy did. But if you have to get all the way to your front door in 1 minute, you have to really book it, right? You have to sprint to get there. Maybe, depends on how big your house is. So this one moves faster, but they both hit the ground at the same time. Those are the two big ideas I want you guys to understand about this scenario. Assuming no air resistance, so when we're throwing footballs around in space, as one does, your greatest range is going to be found when you throw at an angle of 45 degrees. So assuming I'm starting at the ground here, and I'm throwing like this distance, this delta x, is maximized when my angle, my theta here, is equal to 45 degrees. And the reason why is hidden in that range formula that you guys derived with my fellow Beth in this last video. Now, we're still not going to do math. I'm not going to make you guys work out any math, but I am going to write an equation on the board. So I guess I kind of did lie at the start of this video. Our range, our delta x, is equal to v naught squared over g times sine of 2 times theta, our angle here. So to maximize this, assuming we're starting at the same initial velocity, well, gravity's not changing, or at least not without some things going very, very wrong. Gravity's always going to stay the same. So the only thing that we're affecting here is theta. So how do we maximize this delta x? Well, we want to be able to maximize the sine term right here. Sine is biggest whenever the argument, this number that we put inside of parentheses here, is equal to 90, right? If we think about our unit circle, 90 is when we're right here, so sine is equal to 1 when its argument is 90 degrees. That's when it's biggest. So if we want this thing that's in here to equal 90 degrees, that means we're looking for 90 degrees is equal to 2 times theta. So we divide by 2, theta is equal to 45. So if you're playing football in a place with gravity but no air resistance, you probably have bigger problems to worry about. But assuming there is no air resistance, the optimal angle to throw that football at to achieve the greatest range is 45 degrees. All right, those were the 3 big concepts I wanted to cover with y'all today, and y'all hung in there, so thank you so much for sticking with me, and happy physicsing.